All right, we're back here, Physics 1151. This is our final lecture of the week. It's also the final lecture on chapter 25, which is electric potential energy and the potential. So we've developed some of the foundations. Today we're going to calculate the potential due to single and multiple charges. So again, I'll be putting up homework 7 Saturday morning, and it will be due on the 19th, Friday night at 11:59. Quiz 2 will be Monday the 15th, and that will cover homework 6. So the point charge, remember, forms the basis for calculating the electric field and the potential energy of various charge distributions, because any charge distribution can be modeled as a group of point charges, right? And if they're discrete, we sum up the contributions to the potential energy or the electric field. And if it's continuous, we have to do an integration. So similarly, we're going to calculate the potential, V, or the voltage, due to a single point charge. And we have already derived this. So if you have two charges, Q and Q prime, and they're separated by some distance r, there's an electrical potential energy associated with their interaction, and it's a constant times the product of the charges divided by the separation. And that constant, sometimes we use K, which is 9.0 times 10 to the 9. Sometimes we use 1 over 4 pi epsilon naught. It's the same number, so it really doesn't matter. 1 over 4 pi epsilon naught is K, the dielectric constant, where epsilon naught is the electrical permittivity of free space. So we can use either one. It really doesn't matter. It's a constant. Shouldn't have a K there. I'll have to get rid of that. Should only have one or the other. So suppose that charge Q prime is the probe charge. So to calculate the potential at some distance r from a point charge Q, we stick our positive probe charge Q prime there. We calculate the potential energy of interaction of the probe charge Q prime with the source charge Q, and that's just 1 over constant times Q prime over r. And then we divide by the magnitude of the probe charge Q prime, and we get the potential of a point charge, the electric potential. Okay, it's exactly the same way as calculating an electric field. We just stick a positive probe charge Q prime at some location where we want to calculate it. We calculate the interaction energy, the potential energy between the probe charge and the source, and then we divide out by the probe, and we see that the potential only depends on the source charge and on the distance to the source charge to wherever we're calculating the potential. And so this potential exists everywhere in space, regardless of whether the probe charge is not. It's a measure of how much that the source charge Q alters the space around it. And this formula, remember, assumes that the zero of potential, where V is equal to 0, that we set V equal to 0 infinitely far away from the source charge. So we set V equal to 0 at r equals infinity, which physically makes sense, because if you get infinitely far away from the source charge, it's not going to exert any influence on other charges. And so this is the equation of the potential due to a source charge Q, the point charge. Looks exactly like the electric field, except it's a scalar, and the electric field had an r squared in the denominator. And so if we plot this, you see that at some distance 2r from the potential, from the source, you plug in 2r instead of r, the potential is down to 1/2 of what it is. If you plug in 3r, it's down to 1/3 of what it is. And so it goes down faster initially and then slower later on. And we can make contours of equal potential. So in other words, all the points at the same distance r from the source charge will have the same potential. And so we can place this little contour, and all these points have the same potential. You can go to a different radial distance. All of these points at this distance have the same potential, and then so on. And so these equipotentials, these surfaces of constant potential, are spheres in 3 dimensions, or circles in 2 dimensions. So let's do this example here. So suppose you have a point charge Q, plus Q, and here we're drawing our equipotentials here as these dashed circles here. And so the question is, rank the potential differences from largest to smallest. Okay, so delta VBA is the difference in potential between points A and B. Delta VAC is the potential difference between points A and C, and delta BC is the potential difference due to points B and C. Okay, now if we look at A and B are the same distance r from the source, and so they must be at the same, they must have the same potential V. In fact, they're on the same equipotential surface. So the potential difference between point B and point A is 0. Delta VAB is 0. They're both at the same potential. So that's the smallest. Okay, now it's tempting to look at B and C and A and C and to think that the potential between B and C is greater because they're closer together. But that's not true here. Points A and B both have the same potential. Okay, and because they're at the same distance away from the source. Remember, the potential only depends on the distance r from the source. And so since B and A are the same distance from the source and they're at the same potential, both of their potential differences with respect to C are the same. And so delta VAC, the difference in potential between points A and C, is equal to the difference in potential between B and C. And so the main point of this all here is that for a point charge, the potential, the voltage, only depends on the distance r from the charge. And so any sphere of radius r is an equipotential because all of these points are at the same potential. So we also found in chapter 23 that the electric field, if you have suppose you have a charged sphere, and the sphere has a radius big R, and suppose you place a total charge Q on the sphere, and we found that the electric field outside the sphere is exactly the same as if all of the charge Q on the sphere's surface were located at the center of the sphere. And so remember that the electric field of a charged sphere looks exactly like the electric field of a point charge, provided we're looking outside of the sphere. And so the potential is also the same. And so the potential of a charged sphere at some distance r from the center, if big R is the radius, the potential of a sphere looks exactly like the potential of a point charge. Okay, it goes as 1 over the distance from the center of the sphere. And remember again, since only potential differences are important, what we're assuming in this equation is that the location of zero potential is at r equals infinity. In other words, we're infinitely far away from the sphere. Now, spheres are typically a little more important practically in terms of understanding their potential, because many electrodes used in various systems are little balls. They're spherical shapes, and so we need to understand the potential of spheres. It also is pretty impractical to place this potential in terms of the total charge Q, because often we don't know what Q is in practice. But we do often know what the voltage is to which we charge the sphere. So suppose that we have this sphere and we charge the sphere to some voltage V0. Okay, and this is measurable, and so it's more practical to express this in terms of the voltage to which it's charged. So we know that if we charge the sphere to some voltage V0, then the potential on the surface is V0, and the radius is r from the center, and so V0 is Q over 4 pi epsilon naught r. And so in this case, we can solve this for Q. So if we know the radius of the sphere and we know how many volts we charge the sphere up to, we can calculate how much the net charge that's on the surface of the sphere. Okay, it only depends on the voltage to which we charge and the radius. So now we can plug all of this in for big Q and get rid of it in this equation. And we do that, we plug it in, and we get another expression which is often more practical. The voltage, the potential V, at some distance r outside of the sphere, where r is bigger than the radius of the sphere, is equal to the potential at the surface, that's what we charge it up to, times the radius of the sphere over the distance from the center r. And this is a much more practically useful expression if we know the voltage to which we're charging up the electrode, the spherical electrode. So let's do an example here. Suppose we have a sphere, and the sphere has a diameter of 1 centimeter. And suppose that we charge the sphere up to some voltage of 1,000 volts. So the surface of the sphere has been charged to 1,000 volts potential. So the first thing that we're going to do is we want to know, well, how much charge is on the sphere if I know the diameter and if I know the voltage that we charge it up to. So let's do that one first. So again, we use our equation here, right? We know that the voltage at the surface of the sphere is V0 because we charge it up to that. And that's equal to Q over 4 pi epsilon naught times big R. So we solve it for Q. We plug in that the radius is 1/2 centimeter, 0.5 centimeters. The voltage is 1,000 volts, which is 1,000 joules per coulomb. And we plug this in and we get that the net charge on the surface of the sphere is 0.56 times 10 to the negative 9 coulombs. And 10 to the negative 9 is a nano, and so this is 0.56 nanocoulombs. So that's the net charge on the sphere. Okay, now let's calculate the potential at some distance 1 centimeter from the sphere. Okay, now we can use this equation right here. Go back. If we know the potential to which the sphere is charged and we know the radius of the sphere, big R, we can calculate for any distance, little r, from the center of the sphere. Okay, so we plug that in. And if we're 1 centimeter from the sphere, and if the radius of a sphere is 1/2 centimeter, then this little r must be 1.5 centimeters from the center of the sphere. It's 1/2 centimeter to get to the surface and another centimeter further. So little r is 1.5 centimeters, and that's equal to 3 times the radius of the sphere if we want to express it in terms of the radius of the sphere. So here we plug in V is equal to V0 times R over 3R, and the voltage is 1/3 of what it is on the surface, or 1/3 of 1,000 volts, or 333 volts. Okay, so this is a slick little formula here. If we know the radius of the sphere or the electrode, and if we know the voltage we charge it up to, we can get the voltage or the potential at any distance r from the sphere, just using this simple relation. Okay, so now we know that voltage, and now suppose that we take a proton and we release it from rest at the surface. What's the speed going to be at 1 centimeter from the sphere? Okay. So we know, remember the potential, here's the charged sphere. Where are we here? Yeah, there we are. We know that the potential decreases as we go away from the sphere, and that positive charges will move from higher potential to lower potential. So they're going downhill. So we know that the proton will gain kinetic energy, and we know that it will lose potential energy. So we can apply energy conservation, which says that the change in kinetic energy plus the change in potential energy is equal to 0. In other words, whatever potential energy is lost is gained as kinetic energy, just like with gravitational problems. So here V initial is 0 because the proton is released from rest, so that term gets canceled. And we know that the potential difference between the surface and 1 centimeter beyond outside of the surface, we know that the potential decreases from V0 to V0 over 3, so we know the potential difference between the 2 points. We know that the charge of a proton is the same as the charge of electron, 1.6 times 10 to the negative 19 joules. The mass of a proton is 1.67 times 10 to the negative 27 kilograms. And we go through and we solve this for the final speed, and the final speed is equal to 3.6 times 10 to the 5 meters per second. Okay, so when the proton gets 1 centimeter from the sphere, it will have accelerated from rest to 360,000 meters per second. So that's a very large acceleration. So you should be able to, on an exam or a quiz, you should be able to apply this equation for the potential of a sphere or a point charge to calculate potential at any distance away from the sphere, the amount of charge on the sphere, and you should be able to apply this to energy conservation problems. And so this example is a good review for a quiz or for a test. Okay. Now what happens if we have multiple point charges? Okay, we want to calculate the potential if we have several source charges, Qi, where I could be 1, 2, for example, Q1, Q2, Q3, if you have 3 source charges. Well, to calculate the total potential, we just add up all of the potentials due to each of the individual source charges. It's superposition. And this is exactly like we did when we added up potential energies. It's exactly like what we did when we added up electric fields, except it's much simpler than the fields because we're adding up scalars and we don't need to keep track of the vector components. So if Ri is the distance from the ith charge Qi to wherever some point P where we're trying to evaluate the potential, we just sum up all of these contributions to get the total potential. So let's do an example here. Suppose that here's our familiar example where we have the square and we have the 3 charges. And in the upper left corner, the charge is negative 4 nanocoulombs. In the upper right corner, it's equal to plus 3 nanocoulombs. In the lower right corner, it's equal to plus 3 nanocoulombs. And suppose we want to know the voltage or the potential at this 4th corner of the square. Okay, well, what we need to do is we need to calculate the potential due to each of these source charges. So let's start with the upper left charge, Q1. Okay, the distance from that charge and the upper left corner to the lower right corner, we use Pythagorean theorem. It's 3 centimeters square plus 4 centimeters square, square root. So this distance along the diagonal is 5 centimeters. Okay? And the charge is negative 4 nanocoulombs, and we plug in K as 9.0 times 10 to the 9. And when you plug all these in, you get that the potential V1 due to this charge Q1 only is negative 719 volts. Okay. Now we go over here, we go to this 3 nanocoulomb charge, this plus 3 nanocoulomb charge in the upper right corner. That's a distance 4 centimeters away, and it has the source charge as 3 nanocoulombs. So we plug that in. K is 9.0 times 10 to the 9, multiply by 3 nanocoulombs, which is 3 times 10 to the negative 9 coulombs. 4 centimeters is 0.4 meters. And you plug that in, and you get that the potential due to this charge, charge 2, is plus 674 volts. And we can do the same for charge 3, located at the lower left corner. The distance from that charge to where we're evaluating the potential is 3 centimeters, which is 0.03 meters. This source charge has a magnitude of 3 nanocoulombs, which is 3 times 10 to the negative 9 coulombs, and K is 9.0 times 10 to the 9, and we plug that in, and the potential due to this charge Q3 is plus 899 volts. Okay, now the total potential, we just add up the potentials due to each of the source charges. So it's 899 plus 674 minus 719, and we get that the potential at this point is 854 volts relative to some distance infinity from the source charge. So this is a lot easier to work with than electric fields because we don't have to deal with the magnitudes and the angles and breaking it into components. We're just adding up numbers. Okay? So this is an example of a superposition, and you definitely should be able to do this on a quiz or exam. Finally, what happens if we want to calculate the electric potential due to continuous charge distributions? Okay, and if you recall, similar to the electric field, what we do here is we have to sum up the contributions of each of the little elements dq along the source to get the total potential, just like we did the electric field. And so in this case, the potential V due to a continuous charge distribution is the sum of all the individual contributions along the source, and that's K times dq, where dq is the little element of charge divided by the distance of that little element from the point of evaluation. So we have to do an integral when we have continuous charge distributions, just like you did with electric fields, where you had to integrate the contributions. Now, in one dimension, remember that the charge density is the charge per length, and we denoted that with the symbol lambda. And so the little incremental element dq is the charge per length times the incremental length. So it's lambda times dl. And if you have 2d, then the incremental charge dq is equal to the charge per area, which is eta, times the area dA. And if it's three-dimensional charge distribution like volume, the element dq is equal to the charge per volume, which is rho, times the incremental volume dV. Okay, and in 3D this would be a triple integral. In 2D this would be a double integral over the area, and in one dimension it's a single integral over the length. So let's do an example here where the integral isn't too bad. So suppose you have a charged ring, and the ring has a radius r, and suppose it's thin enough that we can treat this as like a one-dimensional strip, which has been a strip of length 2 pi r, which has been formed into a circle. Okay, so we're dealing with a one-dimensional charge density lambda. Let's calculate the potential V, or the voltage, at some distance z from the center of the ring and perpendicular to this point P. Okay, so we're going to have to do an integral here. So what we need to do is we need to set the problem up. And for each little element of charge along the ring, we need to calculate dq. And we need to calculate the distance of that little increment to the evaluation point. Okay. Now for this problem, it's easy because all of the points on the ring are the same distance Ri to this point P where we're trying to calculate the potential. Okay, and we use Pythagorean theorem. This distance Ri is equal to the square root of r squared plus z squared. So all the points have the same distance. So that little r in this integral is just big R squared plus z squared. Okay. Now what is dq? Well, it's dq is equal to the charge per length lambda times dl. Okay. And dl in polar coordinates, suppose that theta is the angle from the x-axis, like in polar coordinates, dl is equal to the radius r times d theta, where this is the incremental angle of this little element of charge. And so in this case, lambda dq is lambda times the increment of length, and the increment of length is r d theta in polar coordinates. Okay, so we plug that in. And now we have this expressed in terms of a coordinate system, and we need to integrate this over all of the charge, or in other words, from theta equals 0, which is the plus x-axis, to theta equals 2 pi. So we do that, and this integral looks kind of scary until we realize that everything in here is a constant. If it's uniformly charged, lambda is a constant, take that out of the integral. Radius of the sphere is constant, pull that out. Big R squared and z squared are constants, so they all come out, and we have a relatively simple integral where d theta, the integral of d theta from 0 to 2 pi is just 2 pi. And so we take that, and then we get that the potential, here's our equation for the potential. So that integral was pretty easy. And we get that the potential depends on the charge density, the radius of the sphere, and the distance z from the sphere. Now if we want, we can write this in terms of the total charge by noting that the total charge is the charge per length times the length of this little strip, this ring. The length is equal to 2 pi r, the circumference. So we can plug in lambda as q over 2 pi r, and we can get this potential in terms of the total net charge on the sphere. So just like we did in chapter 3, we can evaluate this if we get very, very far away. So in other words, z is so much further away, so much larger than r, so that we're very far away from the ring. And in that case, r squared plus z squared is roughly r squared, z squared. I screwed up again. So this is equal to z. And then you get that the potential is, this should be a z in here, I have to fix that, is q over 4 pi epsilon z, and that's just the potential of a point charge located at the origin. So I've got to fix that. That should be, this should be z and z here. I'll fix that in the notes before I upload it. And so if you get very, very far away from this ring of charge, it looks like a point. And so for all practical purposes, you can treat it as if all of the charge is at the origin. So this pretty much concludes chapter 5, okay? Take a look at the learning objectives. I'm going to assign homework 7 again Saturday morning, and that'll be due next Friday night, and then get ready for the quiz on Monday on homework 6. So have a good weekend.